Okay, so I'm going to talk about computational movement analysis, which is a fairly recent research area. There were some results in the 80s and 90s, but I think not until about 10 years ago we started to get a more focused research in this area. And so I'm going to pick a few topics that represents what we're doing in the field. Okay, but I will start to just give a little bit of maybe an overview of the application areas, of the problem areas. So in general what we have is we get some trajectory, and I'm going to talk about that a little bit more later on. And we want to extract and make sense of information from these trajectories, right? So we want to provide just fundamental tools that will help us do some kind of qualitative analysis on these trajectories. Okay, so this is our model we're going to use for the next, the rest of the workshop or winter school. So the locations are sampled over time, and we're going to assume that between every sample we move in a straight line, and we're going to assume that the entity moving between these samples move with constant velocity. Okay, so for example, say this is minutes, so the entity is here at time 0. After 5 minutes he's here. After 2.5 minutes he will be along the straight line in the middle, just in the middle between the two points. Okay, so this is the model we're going to use. There are other models. So there are, for example, the Brown and Bridge movement model, where you have some kind of probability space. So you have the two sample points, and then you have a probability space distributed over time. Okay, but this is not the model I'm going to use. I'm going to use the much easier model. So we get a sequence of sample points that are given as XY coordinates, and a timestamp for all of them. And then I connect the sequence of points with straight line segments. Okay? Good. So first of all, of course, this data can be collected in many, many different ways, right? We have GPS, we can get it from mobile phones, radar. Nowadays, there are so many types of sensors where you can collect this kind of data. And in many cases, in many applications, you get additional information. Right? So, for example, we worked on a project where we were tracking seagulls. And there, the sensors have additional abilities. So, not only do we get the XY coordinates and the timestamp t, but we also get the altitude, we get the temperature at the sample points, we get the instantaneous speed at that sample point, and we get the instantaneous direction at that sample point. However, in the talks I'm going to do in the winter school, I'm just going to assume that we have X, Y, and T. Okay? So I gave a survey talk in 2005. And then I wanted to show how enormous the data was. Right? And then I looked on the web, and I found a lot of projects where they were tracking animals. And you can see that most of them are between, say, 7 and 30 animals that they track. And due to the limitation mainly in battery power, you could only get a couple of samples every day. Right, so this was around 2005. So I gave a similar talk in 2011 and looked a little bit at my experience with the industry and also what is out there. And, for example, we work with football data where the samples are given with 25 hertz. So 25 times a second, you will get the coordinates of every player and the referee. Right? And for supermarkets, they use wireless sensors. So there you can actually set the frequency to more or less whatever you want. And in many cases, they actually put it up to as much as 100 hertz. Right? So 100 times a second, you get a coordinate of the trolley that you're tracking, and the accuracy is about 5 centimeters. And of course, if you look nowadays, like in the US, they track most mobile phones. And there's an enormous amount of mobile phones, right? And in 2011, this was done with roughly 5 minutes interval. So it's an enormous amount of data. And I'm just going to talk about the algorithms, how we can extract information. But of course, there are a lot of other problems, right? How do you store and query this kind of data? But I'm only going to focus on algorithms for extracting information. Okay. So just a few examples, just so you get into to see what we are actually looking at here. So the biggest application area traditionally, I think, is behavioral ecology. So they track, pick any animal, and I'm sure that species have had a sensor on them. So here is, for example, great white sharks, and they track them in South Africa. There you want to see what are their migration patterns. So do they migrate during the winter to other areas? Are there certain times of the year where they're very close to the beach? Are there certain places that they go back to very often? And especially what ecologists are often interested in is what is the region that they usually move in? Right? How can you decide that? Here's another example of elephants. So there again, you want migration patterns. The popular places, also flock movements. So how do they move in a group? How do they migrate in a group? Okay. Here is kind of a different project. So jackdaws, apparently, the ecologist has told me this, so I have no clue. I've never seen this working in practice. But most often they sit in a big tree. And there's a very strict hierarchy within the flock. So there's a ranking of all the birds in the flock. And then quite often they fly out from this tree and in pairs, and they perform a dance. This dance lasts for about 20 to 30 seconds. And the ecologists want to see if this dance corresponds to the hierarchy within the flock. Right? So they more or less want to see if two birds fly out from this tree, does one follow the other in this dance? And does that correspond to the hierarchy within the flock? Here is, so in general, we want to find annual migration behaviors. How do the birds move during the seasons? Can we automatically detect their activity? So, for example, if you track a bird, is it possible to say that during this time the bird is foraging? Is it looking for food? Or is it flying to a specific destination? Or is it maybe just playing around, having some social activities with other birds? And so all this is done manually at the moment. It's done manually by the ecologists. But with the huge increase in data, you would like to do this automatically. And also, like, what are the home range? What are the areas they usually move in? The long-term goals is, for ecologists, you want to detect what is the foraging search strategies. So when does an animal spend energy to get energy? Right? And hopefully we can use the analysis of trajectories to answer, or at least support, that kind of analysis. And what is becoming more and more important nowadays is, of course, how do external factors influence the behavior of animal movements? So, for example, a specific example is the elephants in Africa, where they are growing the cities into the areas where elephants live. But it's not very nice to have a group of elephants stomping through the village, right? And they don't really change their pattern very much. So if there is a house, they will still go in that, use their standard migration paths. Okay. Okay, here we have another example. So this is a football application. So again, we get all the players, the ball and the referee, tracked with 25 hertz. And in this case, you actually get a lot of extra information. So you don't only get the XY coordinates and the timestamp, but you also get all the events. So which player passed the ball to which other player, what is the speed of the ball during that time, and so on. And there you want to do things like, is it possible to evaluate the player's ability to, for example, make a pass or receive a pass? Can you evaluate the player's ability to move into an open area, to be open for a pass? And there you want to detect the frequent movement patterns, maybe detect correlations between different players. So do they move together often? Can we detect frequent passing patterns? And then in the long run, we would like to do, say, analysis of turnovers and other. And what the coaches are very interested in is what are the events that change the intensity of a game. So these are just some of the many questions in computational movement analysis. Here's another one for hurricanes. So you can detect when a hurricane starts, and then what you want to do is you want to say something about the expected probability that this hurricane will hit land. Okay. Here's another example where you track all the ships outside the coast of the Netherlands, and this is is it possible to maximize the utility. Here's the data from the supermarkets, and in general what they want to do is just increase sales, right? So can you change the layout of the supermarket such that people spend more time and money inside the shop? So there are a lot of applications, but there's still a nice set of generic problems, generic fundamental problems. So, for example, we want to find repetitive patterns with repetitive movements. We want to find places that are popular in some sense. We want to segment the trajectory with respect to the activity. Also very important is clustering, right? I mean, clustering for points is used for everything, more or less. And what we want to do is how do you cluster trajectories? And then our movement patterns. Can you detect a flock movement, so a moving cluster? Is that possible to do? And this week I'm going to talk about mainly segmentation, simplification, clustering, and a little bit about movement patterns. Okay, so the seminar schedule is slightly different from what I announced before. So today I'm going to talk about similarity. I'm mainly going to talk about the Fauché distance. Then tomorrow I'll talk about how you cluster curves or trajectories. Then I'm going to talk about simplification. Lecture 4 will be on movement patterns, and then the last one will be on segmentation. Okay. Does that sound okay to you? Good. So, a lot of these fundamental tools, like clustering, for example. I mean, how do you cluster the movement? Right? So say we don't take time into consideration at all. Right? Because most of it, for example, if you want to look at a football player, what is his most common movements? You don't really need the time. It's not how fast he's running. But maybe what is the movement he's doing? So this is an Arsenal player playing on the left-hand side, and he does very often this movement from this region, he moves in towards the penalty area. So you would like to detect that. Okay, so you want to do some kind of clustering, but how do you do clustering? Well, you need some kind of distance measure, right? You need to say that this curve is similar to this curve, or what is the distance between two curves? Right? So when it comes to distance measures, there's a long list of suggested measurements, starting already in the mid-90s and going up just to recently, to last year. And most of them are not metrics, but I would like to try to define a distance measure that is actually a metric. So let's look at a couple of examples. So the very first attempts to measure similarity between curves is this very simple one. So you get two polygonal curves. We get one polygonal curve, and we just look at the vertices. Right? So this has 5 vertices, so we just take each vertex has 2 coordinates, so we can just map this into a 10-dimensional space. So it's just a point in 10-dimensional space. Okay, so now we have 2 curves, and they will both be mapped to 10-dimensional space. And then you do a similarity measure between, so just take the Euclidean distance, for example, in 10-dimensional space. And we say if they're close, they're similar. If they're not close, they're not similar. But of course, I'm sure you can see that this is not a very good idea. Right? First of all, I mean, you can have 2 curves that are very similar, but the vertices of the 2 curves are very far from each other. So here, for example, we have 3 points that are mapped into 6-dimensional space, but because this vertex and this vertex is very far from each other, that means that they will be very far from each other in 6-dimensional space. Right? So they're not similar, even though the curves are very similar. So this, I think this was abandoned very quickly, this approach. So the other one is the Hausdorff distance. So the Hausdorff distance says, say we have 2 polygonal curves, P and Q. Now, for every point on P, so let's define the function h, p, q. Now, this function says for every point on P in P, we take the minimum distance to Q. Right? And then we take the maximum over that. That's our function h of P to Q. So that would be, in this case, we take for every point in P, we take the closest point in Q, and then you take the maximum over that, so maybe this would be this distance here. Okay, and then the Hausdorff distance is defined as the maximum over h to p to q and h to qp. So here we take the shortest distance from every point on P to Q, and then we take the maximum of that. And here we take the smallest distance for every point on Q to P, and then we take the maximum over that. That's the Hausdorff distance. So this seems like a reasonable distance measurement. However, look at these 2 curves, right, and say that they are very close to it. They overlap like this. Now, of course, you can. I just made the distance a little bit bigger to visualize this, but you can imagine that Q is very close to the boundary of P. Now, the distance between every point in P to a point in Q is very small, and the distance from every point in Q to a point in P is very small. So that means the Hausdorff distance is very, very small. But these are obviously not similar, right? So this doesn't seem to work very well either. And there are other very nice distance measures. So there's the dynamic time warping, longest common subsequences, and a new distance measure that was proposed last year that is a mix between dynamic time warping and edit distance, which I think is a very nice distance measure. So I think this deserves a little bit more study. But the drawback of most of these distance measures is that they are not a metric, which makes certain operations a bit complicated. Like, it's a bit tricky to do clustering, for example, if you don't have a metric. Right? Okay. Good. So the next one is, and this is the distance measure we will use throughout the week, is the Fauché distance. So today I'm just going to show you how you compute the Fauché distance, and then in the other lectures I'm going to use this result. So the Fauché distance measures the similarity between two curves. And you can see it as follows. You have the owner of a dog and the dog, and you have the two curves that you want to measure the distance between. So you set the owner of the dog to follow one of them, and he has to start at the start point. And you set the dog to follow the other curve, and he has to start at the start point. And now you want to take the owner and the dog to the end of the curves. And you're allowed to vary the speed of the dog and the person. Right? And what the Fauché distance is the minimal leash length, so the minimum maximum distance. Right? So let's look at this, for example. These two guys, well, dog and a person, they walk along this curve and then they get to these two bumps. Now you want to minimize the maximum distance, right? So instead of letting these two, the person and the dog, walk at the same time, we can say, well, let's let one of them walk first. Okay, so we let the person walk first, and when he's over the bump, we let the dog walk. Okay, and then they walk to the end, and we're happy. So what is the leash length in this example for this parameterization? Well, the maximum distance is probably here when the dog is at the bottom here and the person is over the bump. So you want to minimize, and now you look at all the movements, all possible reparameterizations of the speed along the two curves, and you take the minimum of all of them. Okay, that's the informal definition. The more formal definition is that the Fauché distance between P and Q is the infimum over all reparameterizations, alpha and beta, so you parameterize from the start to the end of the paths, and you take the maximum of all the parameterized points. Okay? And as I said, you have to start at the start of the curve. So you set alpha of 0 to be the first point. You set beta of 0 to be the first point on the other curve. And they have to end at the end of the curve. So the last alpha of 1 has to be the end point of the first curve, and beta of 1 has to be the end point of the second curve. Okay? So it has been argued in many, many papers that this is very well suited for comparison of curves. Okay? And it's also the measurement we will use this week. Okay, there is a version, I'm just going to mention this on one slide. There is a version where, so if you look here, this is a continuous version, right? The person and the dog has a continuous movement along the curves. There's a discrete version where you only look at the vertices. Right, so if you have two curves, you just do a mapping between the vertices, and you want to minimize the largest distance. However, it's fairly easy to give an example where this doesn't work very well. So for example, if you have, this is a straight line segment, and this path is just two line segments, and you can see this doesn't work very well because they're very similar, but since the distance is taken between vertices, there has to be a distance between this point and this point, which is very large, right? So the continuous Fauché distance would be very small, but the discrete Fauché distance is very large. Okay? Good. So now I'm going to compute the continuous Fauché distance. I don't know how, do many of you already know how to compute the continuous Fauché distance? Okay, a couple of you. You can help me when I get stuck. So we get two polygonal chains or polygonal curves, P that has n points and Q that has m points. And they can actually be in any dimension. It doesn't really matter that they're in two dimensions. We won't use the fact that this is in a low dimensional case. And I'm going to look at the decision problem. So I'm only going to look at is the Frechet distance between P and Q smaller than R, smaller than or equal to R? Okay. Okay, so just start to look at this a little bit. So it's only the decision version, right? So these are so now look at a very specific example. So P and Q are segments. Now I'm going to build a free space, what is called a free space cell. So I put P here and Q here. And both of them are scaled, so the distance is 1. The length of them are 1. Okay? So now what I want to do is I want to color this cell in 2 colors. So I want to say that if I color a point white, that means that the distance for that point, let's do it like this instead. If I consider 2 points on P and Q, so 1 point on P and 1 point on Q, then the point on P will correspond to a point on the vertical axis, right? The point on Q will correspond to a point on the horizontal axis. Okay? And now the only thing I want to say is the distance between these 2 points at most R. Right? So this is the point on P and this is the point on Q. Now I want to say this point, are these 2 points smaller than or equal to R? If they are, so if I put a ball with radius R at centered at this point, and it includes the point in P, well, then the distance between them is smaller than R. So the only thing I will do is I will color this point white. Okay? So white means that the distance is smaller than R. Okay? And now I want to do this for all pairs of points on PQ. So let's look at this a little bit. So let's look at the start point of Q and put a ball of radius R. Okay, it will intersect this part of P. So all these points on P will be within distance R. Okay? So that means I'll track this point, and then everything that is below that will be white. Right? Now I start to move this ball, and say I move it until I leave this point. This point, the start point of the start point of P will leave the ball. Okay? So that means I have this point which corresponds to this point, and then I have the intersection point of P and the ball, which corresponds to that point, and then I know that everything here corresponds to this line, and all that will be white. Right? Is that clear? Yeah, good. And now I can continue like this. Now I hit the end point of P. I do the same thing. I put this point here, this point, here, and I can see that everything above is now white. Right? And then I reach the end, and again I can see. So now I have these 4 vertical lines where I know are white space lines. Good. So now look, but what is the general shape of this white space? Because I only took 4 sample points. What is the general shape of this? Well, if you look at what is the function describing the amount, the part of P that lies inside the ball. Yeah, I think you'll see it here. So now we move the ball, right? So it's the intersection between a moving ball and a segment. And this is an ellipsoid function, right? So this ellipsoid, this intersection between the ellipsoid and this cell is my free space. Okay? So for every point inside this white space, So if I have this point here, it will correspond to a point on P and a point on Q, and the distance between those 2 points will be at most R. Okay? Is this clear? Yes, yes, good, good. Good, so this is called my free space, and this is the free space diagram of P and Q. Okay. So how do we find, so this is just saying which points in P and Q are closer to each other than R. But now we want to find a reparameterization. Do you remember we wanted to do a reparameterization of the curves so that the distance between every match point pairs is at most R. So this is our free space. And now we want to see, can we walk along P and Q such that the distance between these 2 moving points is at most R? Right? So recall that this reparameterization has to create a mapping that is continuous, non-decreasing. The first point has to be mapped to the first point. The first point of P has to be mapped to the first point of Q. The last point of Q has to be mapped to the last point of P. Okay, so let's start with the first points have to be matched. So we have to match the start point of P with the start point of Q. The 2 endpoints have to be matched. It must lie in the free space. Because if I go outside the free space, that means that I'm matching a pair of points that have distance greater than R. Right? So that means that the Fauché distance has to be greater than R if I use this parameterization. So I have to lie inside the free space diagram. It has to be continuous. So I can't stop and then jump to somewhere else. And it has to be non-decreasing. So that means that I have to walk monotonically along Q. I cannot go back and start again. Good. So this says if there exists an XY non-decreasing path inside the free space from the bottom left corner to the top right corner of the diagram, then the Fauché distance is at most R. Okay? Good. So let's expand this example a little bit. So now we just had 2 segments. Let's look at the case when we have 1 segment and 1 path. So now we want to build the same free space diagram. So we do it for every pair of segments. So P is a segment, so it only has 1 unit on the y-axis, and Q has 6 segments, so it will have 6 units along the horizontal axis. And again, we just want to decide if the distance is R or not. Okay, so let's do this just sweeping from left to right with a ball of radius R. Okay, so again, let's look at the point set along P that lies inside this ball. Well, it corresponds to this part here. And now we start to move the ball, and we continue until we're not intersecting P anymore, and that creates these 2, this white space. And we continue the sweep, nothing happens, we have a gray area, and then we hit it again, and we just continue like this. Okay, so it's exactly like doing it for 2 segments. It's just now you actually just put them together and do all of them at the same time. Okay. So then we can expand the example even more, and we have 2 curves, 2 polygonal curves, P and Q, and now we build a free space diagram for P and Q. So again, P is on the vertical axis, Q is on the horizontal axis. And again, we want to find a non-decreasing path in the free space, starting from the start point, Q1, P1, going to the top right end point. We have to start at the start point and end at the end point. Okay? We build a free space diagram, and the only thing we want to find is there a path in this free space from the bottom left corner to the rightmost corner, top rightmost corner. Yeah? Is that clear? Yeah?
The existence of such definition problem of yes or no.
Yeah, because if there's no such path, then that means that you have to cross over. Your path has to cross over a gray area. And if you cross over a gray area, that means that that point, that corresponds to a point pair on one on P and one on Q, and the distance between those 2 points is greater than R. Right? And since the distance is greater than R between those 2 points, the Fauché distance for that parameterization would be greater than R. Okay?
Is there any rule that specifies this free space in the diagram, the white colors, located such a way that we have a path from one to another and one to another? Do we continuously shape up the right area? Is it
So in general, if you so what you can say is if I increase R, right? If I increase R, what will happen is that these white spaces will grow.
I was asking about the continuation between each white area, in a way that we can find a way from the starting position to end position in white areas. I think it may be the discrete form of white areas.
Yes, I will actually come to that later on. But you have a good point. So we'll look at events when you will have a path and when you won't have a path, and what kind of events that is. I will do that in a minute. Okay, so in this case, I found an XY monotone path in the white space. Okay, so if my R is this, then this is the free space, and there is a little bit of a white space tunnel here that I can use to get an XY monotone path. So what does that actually mean? Well, it means that I can move 2 points along P and Q, such that the distance between these 2 points is never greater than R. So let's look at the first edge along the XY monotone path. It's horizontal. So what does that mean?
If you just the dot stay and the person walks.
Exactly. Because I'm not going up along P, right? So I'm only moving along Q. So this is the movement for the first segment. Then in the second segment is horizontal. So then I'll do the opposite. I'll move along P, but I'll stay put at Q. Okay, so now I'm here. And the third segment, I move both of them. But I move one whole segment along Q, but I only move a little bit on P. Right, so it will look something like this. And then I have an horizontal segment, so I will move only on Q while I stay put on P. Now I'm here. Now again, I move quite a lot on Q and just a little bit on P. And where am I now? I'm here, right? And now I move more or less with the same speed for both of them. And now I'm here. And now again, I move only on P. So I stay put on Q. Then I move only on Q and stay put on P. And I continue like that. And since this path lies entirely within the white space, that means that the distance during this motion between the 2 points was never bigger than R. Right? So that means that this parameterization realizes a Fauché distance that is at most R. Okay? Good. So now we have to, okay, now I just showed you how you do it. But how do we actually do it? How do we actually compute this? Okay. So we can compute the free space diagram in m times n. So I'm saying more or less that for each cell we can do it in constant time. Right? It's just the intersection between an ellipsoid, and a square. Okay. So it can intersect in at most 8 points, and these are what we call critical points. Since this ellipsoid is convex, the free space in this cell will be convex read. So we can easily compute it in constant time. Okay? So, well, I said easily, but of course you have to actually have this function that defines the ellipsoid function. But for our setting, we don't really need the exact convex shape. Right? Because here, if I want to go from this point to this point, I don't really have to go into this area. Right? So I can actually make it much easier. I can just more or less cut off the convex regions and replace them with just straight line segments. So this is easy to do, right? So I just take the start point of Q, put a ball of size radius r. That will give me this point. Then I take the end point of Q, put a ball of r, see what I get on P, and then I get this point. And then I continue like this. And I will get, using this, I can get all the points that I'm interested in here. Okay? So, if P has complexity n and Q has a complexity m, then the total time to build this free space diagram is m times n, because every cell I can compute in constant time. Good. Okay. And these are my critical points. So next I have, okay, so now I have this free space diagram. So how do I find an xy monotone path? So I want to find an xy monotone path from Q, from the bottom left point to the rightmost point. Any suggestions how I would do it? Exactly. I can just more or less grow from here all the places I can go to, right? So I start at the bottom left point, and what can I reach from there? Well, in this case, I can go up to this critical point. I can go up to the corner here. I can go to this critical point and this critical point. Okay? Now, for each of these points, I just continue in the same manner. So from here, I can go here. And I guess I could even have gone here. I can go up. And I can reach all these critical points. So now, let's say that I want to go from... Let's say I want to go from here and up. So can I reach this point, for example? No. Because I have to do it monotonically, right? I have to do this x monotone. So now, when I get to a point like that, I have to be a little bit careful. So, for example, here, this point might be higher than this point, but I'm not allowed to go down. So that means that I have to predict this point and go to the lowest point that I can reach. Okay, so just continue growing this, and then from there I continue growing. This point can reach these 2 points. I continue, and then so now I have a graph, right? That tells me where I can go from and where I can go to. Okay. And now I just do depth first search more or less. Right? I just start here and I just grow a shortest path. Right? Well, you all know depth first search, right? So I just start here and now I just see where I can reach using y monotone edges. Okay? So the number of edges in each cell is only constant, right? Because I have at most 8 critical points. And since I have m times n cells, that means that the size of my graph will be m times n. And each edge I can just compute in constant time. Okay? And then running breadth first search in this graph will just take me linear time with respect to the network. So that again will only cost me m times n. Okay? Good. Is that clear how we did the decision algorithm works? Yeah. So we'll use this quite a lot. So if anything you're missing or anything you don't understand, please let me know. Okay, so the decision algorithm you can compute in m times n time. Okay, so given 2 polygonal curves and a radius r or a value r, one can decide in m times n time whether the Fauché distance between p and q is at most r. So now the tricky thing is, this only gives us a decision algorithm. How do we actually compute the Fauché distance from this? So we want to do some kind of search on R. Right? But R could be just any real value. Right? So you can't really do any binary search on it. So is there anything we can do binary search on? So say that I would be happy with some kind of approximation. Say I would be happy if the accuracy is, say, 10 digits or something like that. Can I then do binary search? Yes, right? Because then I could just determine R bit by bit. And so I guess a value. Then I run the decision algorithm. The decision algorithm says if it's smaller or bigger. And if it's bigger, well, then I just try a 1. And if smaller, I just try 0. Right? So then the decision algorithm takes m time, and I have to do binary search on the log of the accuracy. So this is usually how it's done in practice when you do this. But, of course, we are theoreticians, right? So we would like to have something better, more accurate than this. So now I'm getting into a little bit what you were talking about. How you actually, what happens? When do these? What kind of events affect when I will get the path, an XY monotone path? So assume that I set the Fauché distance to be 0, right? And now I start to grow this radius, this distance. So this is like I take this ball and I start to make it bigger and bigger and bigger. Okay? So that means that the white space in my free space will become bigger and bigger and bigger. It will take up more and more part of my free space. Okay? So what are the events that affect new passages? Right? Because there could be passages I can't go from one row to another row, for example. But then at some point there is an opening between the 2 columns that I can pass through. So when does this happen? Well, so there are 3 cases. So one is when the radius, the Fauché distance is minimal, when the distance between the start points is exactly the Fauché distance, right? So anything smaller, well, because the start points are too far away from each other, I can't find a Fauché distance that is smaller than the distance between Q1 and P1. And equally, the Fauché distance cannot be smaller than the distance between the 2 endpoints, right? The other one is the Fauché distance is minimal when there is a new vertical horizontal passage that opens up between two adjacent cells. And I'll show you what it means. And finally, the differential distance is minimal when a new vertical horizontal passage opens up between two non-adjacent cells. Okay? So look at these. Okay, so the first case, of course, is easy to check, right? If the distance between the two endpoints is smaller or greater than r, right? So we can do that in constant time. Let's look at case 2. So here we have a radius r. So we guess a radius r. And now say we start to grow r. So what will happen is that this free space, white space, will start to grow. Right? Oops. So we might have critical points here, but then we can't do anything. We can't go anywhere. But at some point, this radius will grow so much that it will hit this boundary. And this opens up a passage to the next cell. Right? So we get a new passage here, and from these two critical points, we can now go to the next cell. So this is an event, right? Because all of a sudden the structure of the network changes. Okay? So how many events do we have of this type? Well, how many times can it happen for one cell? A constant number, right? One for each, because this is convex. The only thing that happens now when we increase this is that this passage will be bigger and bigger and bigger. So we can have 4 of them. And since we have m times n cells, that means that the total number of events of case 2 is m times n. Okay, so that's fine. Now the tricky thing is case 3. Right? So here we have a critical point here, but then this critical point is below. So we can't really go, we can't go from here to this cell here. Okay? Because I cannot go down. And if I go, take the horizontal path, well, then I will hit this boundary. And I'm stuck. Right? I can't go below that one. But now what happens if I start to grow R? Well, if I start to grow R, this white space will grow. And that means that these tops will start to, this one will decrease, and this one will increase. Right? So something like this would happen. And at some point, these have the same value. And that opens up a passage going from this cell to this cell. Right? So what are the number of events in this case? No, it's more actually. So how many of these can you have? You can have n times m of these. And how many of these can you have if I fix this one? Well, I could have all of them, right? So I have nm of these, and it can happen that I have n of these. And of course, I could have the same on the other side, right? So the number of events is m squared n plus m n squared. So of course, this is huge, right? So this is not really a very good result. So I will start to speak very slowly now because I realize I'm going way too fast. Okay. So, say we perform binary search. So say we compute all the events, right? We can easily compute exactly when we hit this boundary. We can easily compute exactly when these two are the same. Okay? So then we can just pre-compute all of them, which we can do in m squared n mn squared time. And then we do binary search on that. Okay, so this is really bad. Now there's a very nice technique called parametric search. So, do any of you know parametric search? Okay. So I would have loved to talk about parametric search, but parametric search is actually quite hard, and it would probably require another 2 lectures just talking about parametric search. But the idea is that you get all these event points, right? And what we do now is that we pre-compute all the event points. We sort them, so that's why we'll have to pay all this. And then we do binary search on these event points, right? So there is no real way we can get away from this if we have to pre-compute all the event points. So then there is this very nice result by Megiddo in 83, and then this was improved in 88 by Cole. That more or less says, instead of pre-computing all the events, we actually run the algorithm, and every time the algorithm makes a decision, depending on the value of R, we split the algorithm. So we just implicitly compute all the event points, but we only compute them when we actually need them. Right? So the very nice result by Megiddo and Cole is the following. So we have a decision version that says if the Fauché distance is smaller than R or greater than R. It depends on the parameter R, and it is monotone, right? If I know that the Fauché distance, if I know that the decision version says yes for some big R, then it will say yes for every R that is bigger than that. And if I know it's no, then I know it will be no for all the values of R that is smaller than that. Okay, and what we want to find is a minimum Fauché distance such that the decision version will return true. Okay. So our algorithm is sequential, and it can solve this decision problem in mn time. Okay. Now, what Megiddo and Cole showed, and this is very simplified, it also requires some constraints. It says that if there exists a parallel algorithm, A of P, so it's just a parallel version of this, that can solve the decision version in TP time using P processes, then there exists a sequential algorithm with running time this. So the number of processes, the running time of the parallel algorithm, the running time of the parallel algorithm times the running time of the sequential algorithm, plus the running time of sequential algorithm log P. Now, it's not very hard. Well, it's not trivial either. But what you can prove is that the sequential algorithm, the parallel algorithm for this, is equivalent to just sorting n numbers. So doing a parallel sorting network. And this we can do with n processes and log n time. And if you just plug this in, that means that we get n processes, log n time plus mn, and then mn log n. So the only thing we get is mn log mn. Okay. So if you don't know this technique, you don't have to read the paper you have to read the paper to understand it, but it's actually written in a very nice way, so that you more or less can just plug in your problem. If you have a decision problem that is monotone, you can more or less just plug in this result. So if you do some kind of binary search and it takes you too long, look into this and maybe you can just apply it. Good. Okay. So again, we have these three cases, and then we do parametric search on case 3, and we get mn log mn time. Okay, so just to summarize lecture 1 a bit early, but I'll do it anyway. So there are many, many different similarity measures. And what we will use in this winter school is the Fauché distance, which I think is probably the most accurate distance measure for curves. The drawback is that it's a bit slow, right? So it requires more or less quadratic time to compute it requires quadratic time to just decide if the Fauché distance is at most r, and we can compute the Fauché distance between two curves in mn log mn time. So it's slow but accurate. So there are a lot of nice open problems here. So the most important open problem is, can we do it faster than quadratic time? Right? So the current best bound is something like order mn log mn divided by log mn. Right? So in the original paper from Alt and Godot, they conjectured that the problem is three-sum hard, which implies that it's probably not possible to do it faster than quadratic. But then in a recent paper by Buchen and al., they actually show that this is not so clear. So at the moment, we have no clue at all. We don't know if it's possible to do it in faster than quadratic time, or if we believe that there is a quadratic low bound. Right? This is probably the big open problem in this area. And even the problem of, can you even approximate the Fauché distance? So say I want to just have a constant approximation factor. This is not known how you can do this in subquadratic time. However, there are a lot of special cases that you can do a little bit faster. Well, not lots, but there are a few. So if you assume that the curve is C-packed, and what do I mean with C-packed? Well, so say I have my curve, so one of the two polygonal curve. Then I say for every ball of ball B, if I look at the part of the polygon, part of the path that lies within that ball, it's not allowed to be too big. Okay? So it says for every ball, the part of the path inside any ball B has to be at most C times the radius of the ball. And if this is true, then I'm saying that the input is a C-packed curve. Now, if the curve is C-packed, then I can find a 1 plus epsilon approximation to the Fauché distance in roughly n log n time. Okay? And there's a similar argument saying that it holds for the case when you have low density. Okay? So I think this is a very, very nice result. I was actually planning to talk about it, but I thought it became a little bit too complex. So, but if you want to read a very nice paper, I think this is one of the nicest papers in the field. Okay. But, I mean, this is a 1 plus epsilon approximation. I think, if you could just come up with any constant factor approximation in subquadratic time, that would be a very, very nice result. Okay. So what I've mainly been using today is the original paper by Alt and Godot that showed how you can use this free space diagram between two polygonal curves. That was in 1995. Then the currently fastest algorithm for computing the continuous Fauché distance is by Buchen, Möllmans, and Mulzer. And they proved this bound, right? So it's still more than quadratic time. Right? So it's square root of log n and then log n to the power of 3 over 2. And they argue also that this conjecture that the problem is three-sum hard, it doesn't really hold. The argument does not really hold. So I think it's completely open if you can do it in subquadratic time. Before, I think it was more or less assumed that you cannot do it in subquadratic time. But now I think it's completely open if you can do it or not. And if you want to look at how you do parametric search, there's a very nice paper by René van Oostrom and Remco Veldkamp that show how you can do parametric search made practical. Okay. So I'm a little bit early. So I did a couple of slides on parametric search, but I still think it's a bit too hard. And maybe this late in the afternoon, I think it's going to drain you completely. So I think we'll just stop here. Thank you. Any questions? Yeah?
Kind of I can understand that how we can compute critical points of case 1 and 2.
Yep.
But how we compute critical points of case 3?
How you do it? So, I mean, if you use the brute force algorithm, then you just look at every... This is just a value that depends on R. Right?
Yes.
And this is just a value that depends on R. So now you only check when you have two, what's it called? Two formulas, and you just see when they coincide.
So you don't need to continuously...
Exactly. I don't need to consider. I can actually just compute it directly when they will coincide or not. And that's why I can use a sorting parallel network, because if I look at the sorted point set, right, then these two will coincide exactly when 2 points that I'm sorting have exactly the same value.
So you check all the formulas for all mn squared in one row or in one column.
Yeah. Yes. Any other questions? No? Okay, good.